Okay, what's good, gang? Today on the menu, we're gonna do enthalpy. So we start with endo versus exothermic, which is coupled with to heat. So what we covered last time. Here, last time was heat. That heat is the energy transferred. So transferal of that temperature. So heat transferal, we can either have endothermic or exothermic reactions. Then we talk about enthalpy, drawing enthalpy within these graphs, and also relate the concept of enthalpy to endo or exothermic reactions. So endo or exothermic reactions, we should kind of be familiar with these. We draw these out. We have two different reactions, endo and exothermic. We have this one, which I hope you realize is exothermic, and then we have another one that is endothermic. And so the difference, probably you can already tell, is that one is starting at a high point and ending at a low point. And these are energy, and then their direction of reaction or time as we go this way. Bada bing, bada bang. Energy increases as you go up, and the reaction progresses as we go to the right. So this is talking about chemical reactions that are happening, and they can either be endothermic or exothermic. And what does that mean? Exo means as in exoskeleton. Exo means on the outside of something. So let's say you're a little turtle, then you have your little shell on the outside. Yeah? That means exo, outside. So exothermic also talks about that heat is released toward the outside. So you have heat being released. Bang! Heat released. Oh. Because it is exothermic. So energy is going out. Then endothermic would be the opposite, right? Endothermic is that heat is not released, but it is absorbed. So heat here is absorbed. And how can we see these phenomena in our graph? Let's see what we can see. So here, over here, what do we have? This is our reactants. What does reactants mean again? That means what we are putting into our chemical reaction. So if we have a chemical reaction, there's going to be something here, a molecule here. That is our reactant. And then there's going to be something over here, let's say H2O. That will be our products. And where do we find those? Those are down here. Our products are at the end when it's plateauing again. So products are at the other side of the arrow. Reactants are before the arrow. Products are at the end of the arrow, what it turns into the product. So you can also see that as like a factory, the product of the factory. So those are those 2 points that we need to know. We also have this thing over here, the distance from the top of my graph to the energy of my reactants. And this energy is called the activation energy, or EA, activation energy. What does this mean? As the name suggests, it is the energy needed to start or activate the reaction. Energy needed to activate the reaction. Okay? You can imagine this, that if you, let's say, our reaction is talking about that we have wood over here as my reactant, and then being turned into partially CO2. That would be my product, sorry. So my reactant here in my reaction is wood, and then once it's burning and once it's reacting, it produces CO2. But as you all know, wood just doesn't spontaneously ignite and turn into CO2. We need to actually give it some energy in the form of a lighter or fire, and only then can the reaction start. Right? Reactions don't start out of nowhere. They need a little push, a little bit of activation energy to start the reaction. And that is what we see here. And then we see that there is a discrepancy between the energy of our wood. Let's say that is 100 joules. Our wood has 100 joules on the energy. And here we see that we've gone lower. Our CO2, let's say, only has 50 joules of energy left. Where did that energy go? Because we know it cannot be created or destroyed, so it wasn't destroyed. That's impossible. Instead, what happened, this is our heat released. The difference in the energy of the wood and now the energy of the CO2, that 50 joules, this difference over here, is now released as heat. Okay, so to recap in a clearer drawing, this would be it. Here we have our reactants, so that would be before my arrow turning into here my product or products, because there can be multiple. The energy from the top here, from my starting energy, that is my activation energy, the energy needed to activate the reaction, and then from my reactant to product is the heat released. Okay, heat released. Cool. The same goes for this graph over here, right? We have, I'll make it a bit clearer. We start low and we end high. Again, this is energy and this is time or reaction progress. We have the exact same points. Here is our reactants, here is our products, right? We start with a reactant and we end with a product. Start with a reactant and that turns into a product. Here as well, we have our activation energy, all the way from here to the top. That is the energy needed to activate the reaction. And then we also see our difference from the energy in my reactant to the energy of my product. So this could be, for example, C2H6, ethane, being turned into CO2 and water. Just kidding, because that is completely exothermic. So that is not a good example. That is my bad. So we have something with low energy starting over here, being turned into something with a higher amount of energy. So here, this is our heat absorbed to make that happen. Okay, so endothermic, heat absorbed. Exothermic is heat released. Cool, that's those two. Then let's continue with enthalpy because they are very closely related to each other. So we have something called chemical energy, right? Chemical energy is, by definition, is the energy stored within bonds of a chemical. And so here we have our bonds. This is where the energy is stored. It's not stored in my oxygen or my carbon or my other oxygen. It is stored in the bonds that keep them together. That is my chemical energy. Yeah, it is the energy stored in bonds. In B-O-N-D-S. Energy stored in bond. That is my chemical energy. Youpee! And what is enthalpy then? Enthalpy is the total amount of chemical energy within a molecule. So enthalpy is the total amount of, I'll just write EC as chemical energy, total amount of chemical energy in a molecule. Okay, so that is, let's say we have a molecule of H2O. Then the enthalpy of this is this bond and this bond. That is the total amount of chemical energy in my molecule. And the unit for this, for those interested, is kilojoules per mole of substance. Yippee! Usually then we can say something about if something has a high enthalpy, and also the symbol for enthalpy is H, so that I don't have to write it all the time. Let's erase that. So we can say if something has a huge enthalpy, that means that it has a lot of chemical energy. So it has high chemical energy, such as a log of wood, right? That one has a lot of energy because there's a lot of strong carbon bonds within it. Okay, so wood would be a good example of a high chemical energy, aka a high amount of enthalpy. Same with hydrocarbons. If we have C3H8, for example, this bad boy has a lot of chemical energy within it, because if we draw it out, we see that it looks a bit like this. Well, not a bit, it does look like that. H is all around here that I'm not going to draw. And we see that there's now a lot of different bonds. And if we remember the definition of enthalpy, that means the total amount of chemical energy. And this bad boy has quite a lot. Yeah? So high enthalpy means a high amount of chemical energy. And then we can say the same if there's a low amount of enthalpy. This means you have low chemical energy. So for example, H2O, not the most enthalpy in this puppy, right? Or HH, not that great. Okay, that is enthalpy. And then we can also talk about something called delta enthalpy. And if we remember what delta means, it is difference. Bang. So the difference in enthalpy. So for example, let's say I go from wood to CO2. And let's give my wood 400 joules of enthalpy, and my CO2 only 100 joules of enthalpy. So we've gone from a high enthalpy to a low enthalpy, and now my delta H is the final 100 minus my initial 400, which is equal to minus 300 joules. Joules per mole. Okay? So here we see that there is a difference in the amount of energy within the bonds, but where did that energy go? We have a discrepancy here of 300 joules. What happened to that amount of energy? I hope we connect the dots now that this is then released as heat. So this is how delta enthalpy comes into play with our endo and exothermic graphs over here. That this heat released is the same as our delta enthalpy. Yeah? The difference in the chemical energy from wood to CO2, that 300 joules, is what is released as heat. And then the same here, the heat absorbed here is also delta enthalpy, the increase in this case of chemical energy. So that is enthalpy. High enthalpy, you have a lot of chemical energy. Low enthalpy, low energy. And if we do delta H, we can see the difference in enthalpy between our reactants and our products. So let's draw enthalpy now within our two graphs. Here we go. Exothermic. So we have here reactant, here product. Let me just draw it. Product, reactant. Here activation energy. Up to the top is activation energy. And then this difference right here is our delta enthalpy, which is the same as the heat that is released. Yeah? So for example, we go from something that has 400 joules, we stick it in a fire, activation energy, it starts doing, and it turns into something with only 100 joules. There's a difference, a delta enthalpy of 300 joules, and that is released as heat. So this heat released or heat absorbed in the case of this is the same as our delta enthalpy. Here again, reactants, products, my activation energy over here, and then this distance is both delta enthalpy, the difference in amount of energy, as well as the heat that is absorbed in this case. So here we see an increase in enthalpy. So there's more energy within the bonds. And we didn't just get that out of nowhere. No, we got it from heat that is being absorbed. One of an example can be the boiling of water. Yeah, we have just 21 degree water over here. And if we start boiling it, what happens to it? Its temperature goes up, and the amount of energy within those bonds between the H2Os is going to increase. Okay, so that is going to be an endothermic reaction. This also means that our delta enthalpy is a positive. So there's a positive number over here. An endothermic reaction has a positive delta H because we are increasing the amount of energy in bonds. So a positive difference in enthalpy. We are increasing the energy in the bonds. And then here we are decreasing the energy within the bonds. We start, let's say, at 400, end at 100. So our difference here is minus 300 joules per mole. Yeah? So a negative delta H means you are an exothermic. Positive delta H means you are endothermic. Yippee! Is that it? Let's see. Yeah, so that's how it relates to exo and endothermic. Yeah, I think that's good. So here also just some example. Let's say we start with 100 joules and we end with 300 joules. That means that our delta enthalpy is 300 minus 100, and that gives us an answer of 200 joules per mole. And so this is a positive number, which means that it is exothermic. Oh my god, which means that it's endothermic. Yep. Positive delta H, endothermic. Negative delta H, exothermic. And this delta H, the difference in the chemical energy within the bonds, is the same as heat released or heat absorbed. Okay? Cool. All right, bye.